So as you mentioned, I'm Gordon Poch. I'm one of the 3 authors of this paper from the University of Malta. The other 2 authors, Joshua Ellul is also from the University of Malta, and Shaun is from the University of Gothenburg. Much of the work that I'll be presenting today was done actually by Shaun Azzopardi. Unfortunately, couldn't make it, so I am presenting much of the work on our behalf, but mostly on his behalf. So the work I'll be presenting mainly in this talk is some recent work we've been doing on the runtime verification and runtime monitoring of business processes across different blockchains. So to start off, I'd like to motivate a little bit what the context in which this work was done and what has already been done and where the interesting challenges lie. So business process modeling has long been accepted as a very important thing to do when you're trying to understand, when you're trying to document, when you're trying, perhaps most importantly of all, analyze business processes. And by analyze, what I really mean, are things being able to identify, for instance, conflicts between different processes, being able to identify bottlenecks, being able to identify dependencies between different parts of process, and perhaps even dependencies between the different parties in the processes. And modeling such business processes, in fact, typically requires the analysis of processes being carried out by different parties, and this is, I think, one of the big challenges when one tries to model complex processes, where you've got different parties who have different obligations, different rights, different responsibilities, and all essentially, from a computer science perspective, one can see it as an interactive system where you've got a lot of dependencies on processes that require certain information, certain data, certain control input from other agents or parties. And this becomes even more important, I would say, when one has to take into consideration exceptional behavior. For example, if you're looking at another process, another party that should send you some information and that does not arrive, or the wrong information arrives. So handling, in a holistic view, such complex processes can be quite tough. Just to give a very simple example, this is a small business process. The thing is that these processes can grow, these descriptions can grow very quickly. I mean, this is, just to give you an idea, a very simple process where you've got 2 different parties reaching out to each other to agree to sign a contract. And you've got the 2 different parties where one is making an invitation to treat, the other can show willingness to go into the offered agreement or negotiate a different agreement. So you've got this type of thing where you might have a third party, for instance, also trying to support the process, for example, by verifying the capacity to contract by the different parties. As you can see, even such a simple part of a process can grow in complexity very quickly. Here we see 3 different, this notation is BPMN, business process modeling notation, where you've got these so-called swim lanes describing the behavior or the processes inherent in the different parties involved. You've got an initiator, an offeror, and a contract process in the middle. And you've got different, for example, coordination points or communication points across these different swim lanes. Thing is, if the business process that we're describing focuses primarily on a single party, right, where most of the work or the part that we want to digitalize is occurring just in one of the parties, I mean, it's typically not such a hard problem. Okay, so if we've got just one party, or if the different parties all belong or all are part of the responsibility of a bigger entity, say departments of a single company, or if most of the parties are used just to provide some information, then digitizing such a system where you essentially have a single party process can be relatively easy, because this is a well-known problem. People have looked into this and have automated ways of digitalizing such processes. Thing is that if you want to run this, you just need a platform which is controlled by that party, and you can read and write data from other third-party providers and execute the business process without any problems. Things start becoming more interesting when you've got processes that run across different parties and you want to digitalize the process, not just of one party, but perhaps the whole process where you've got the different parties interacting together. Even more so where you need that some of the process logic, some of the things that one of the parties or some of the parties are doing should be transparent to other parties. So when we want to do this, we need something, we need a way of executing such behavior in such a manner that all parties involved can be involved in the process, can also have the transparency required to view and see what is going on with other processes of other parties on which they depend. And okay, if the different parties can agree on a third-party platform, for instance, on which the process will be executed, this is fine, this is easy, this is, once again, we go back to the previous problem, but if not, we've got a challenge, we've got a problem of trust. And this is just a short sidetrack for perhaps, a one-slide quick intro to blockchain and smart contracts and how it fits into the rest for those of you who might not have had the time or opportunity to look into the technology. When the challenge is one of trust between different parties, blockchain technologies or distributed ledger technologies, usually or sometimes do provide the means to handle this. So the idea is that, well, first of all, blockchains and DLTs have been developed precisely trying to address the challenge of removing centralized points of trust. And typically, what you have is a peer-to-peer network, underlying network, where without having any single point of trust, any single party, you can validate and record in an immutable way crypto asset transactions. Party A sends 1 Bitcoin to party B, or and perhaps even more relevant to this talk, the execution of logic or of code in a manner that no single party can interfere. So if there is a process implementation that we want to execute in a manner that we want as one of the parties to be sure that no other party can interfere with the process execution, smart contracts provide precisely this type of mechanism. So the idea is that they're being run on this underlying peer-to-peer network on which the blockchain protocol operates. And the important thing is that, well, there are certain guarantees, certain invariants that you're guaranteed that no single party or no minority can actually interfere with such execution. So this provides a reasonable way to address the challenge that I was talking about in the previous slide. So when we're looking to backtrack to what I was saying, when we're looking at processes spanning multiple parties, and when you've got process logic that has to be transparent to others, in fact, in the literature, one finds various use of blockchain-based smart contracts to operationalize business process models. So the idea is that when you've got a business process model going from one party to another, you can do it on a smart contract to execute, to operationalize the business process model, ensuring that the behavior is according to the business process model we started off with agreeing upon. So things would typically start with an agreement, possibly looking something like this. This is, again, a small agreement handling a procurement process. You've got a buyer, you've got a seller, supplier and a purchaser, and possibly other parties. In this case, you've got secondary parties, such as, for example, the courier. You've got an escrow that can handle funds between the different parties to ensure that funds are passed on when things are delivered, for instance. And from such a description, one can go to a business process model of the sort where you've got, as I was mentioning earlier, you've got different parties involved. I mentioned 4 different parties. You've got the buyer and the supplier, but you've also got the escrow party and the courier. And once again, for instance, the whole process, if you see, would start by the buyer sending a deposit, which the escrow receives, and then the supplier providing the performance guarantee, and the process would continue according to the previous slides explanation in English. And if we want to run this on a smart contract platform, on a DLT, one could very easily or rather use techniques to transform such a model into executable code. I mean, this here is just a snippet of code in Solidity, the most commonly used smart contract programming language probably out there, to encode the behavior shown in this model. And there has been quite a lot of work by different people taking slightly different approaches, using variants of how to do the translation, of how to handle the process, going from business process models down to smart contracts. The thing is, this does not always work as ideally as one would like. So to give a little bit of context, at one stage we were working on a project working on logistics in the maritime industry, and there are quite a few peculiarities in this domain. For instance, not only do you have different parties, but you've got multiple parties across jurisdictions. Each party has their own regulations they have to satisfy, so things become very complex very quickly. Also, you've got different types of parties, so you can have port management, you can have shipping management, customs, etc. And each different party plays a very different role in the processes that we're describing. It is a domain rife with paperwork and permits, so there is a lot of communication between the different parties and recording of information. And what is interesting, perhaps, is that there is quite a lot of work on operationalizing parts of the process. So there is work both on centralized systems, centralized database systems to handle, for instance, certain shipping information. And there are also some blockchain-based solutions to handle parts of the processes. For instance, tracing of containers between certain shipping companies. So this sort of partial solution does exist out there. And the first reaction was great. So what we can do is we can take some of these and build on top of them a solution that would cover the whole domain. However, we noticed that there is one big problem here, right? And the challenge is what we were calling the islands of trust. So in each of these processes that have been formalized and have been operationalized, what we have is you've got an area of trust where you've got things, for instance, being recorded for part of the process on the blockchain. But the problem is that as soon as you leave that area, you lose you leave that island of trust, possibly going into another island of trust. So the challenge was how to put these things together. And it's not just as straightforward saying, okay, we can develop a general solution and assume that everyone will use this. So really the problem was one of interoperability. And in particular, it's not only interoperability between multiple blockchains, but also the fact that it is a heterogeneous network where you've got different blockchains, you've got different types of systems, centralized systems, manual systems, etc. And what we're trying to see was how we can handle such situations. So we'll go back to the business process model that we saw earlier on. One of the things we could have in such a model is that we could already have some annotations. For instance, in the escrow part where the payment is being done, this could be handled via cryptocurrency, for instance, and therefore one could have this being deployed on the public Ethereum blockchain, where people could run smart contracts executing this part of the process and allowing for funds to go in and out of this process. Then again, some other parts, for instance, the courier service could actually be on a separate instance of Ethereum being run, perhaps a private instance of Ethereum, or perhaps another public instance of Ethereum, where they're handling their delivery and proof of delivery separately. It could also be a separate smart contract on the main Ethereum network. Once again, one has to handle interaction between the two. Then again, you can have other foreign parties handling processes. For example, the supplier might have a private blockchain handling their part of the process. The buyer might have their own system, which might be a closed, centralized system, or might be an open one running once again on a private blockchain with limited visibility to the outside world. Again, here for simplicity, we're just having a whole swim lane in one in one location, but one could actually have migration of processes here going along the same swim lane. So the approach we took was starting with such a cross-blockchain business process description, this business process model, as we've seen here, with annotations as to what will be carried out or what should be carried out where. And from this, we can generate automatically smart contracts describing and executing the different parts of the process, of the business process, depending on which blockchain or on which platform the different parts will be executed. These different parts are the different islands of trust, if you will, and you can have different, and you can have a trusted notary then managing the flow of trust between these. This is a standard technique being used when one has to have communication, trusted communication between different blockchain systems. The thing is that it's very easy to develop a solution like this and have an executable version of a business process model like this, but you'll get no buyer who is willing to put their business process to be automatically operationalized and executed on a blockchain or on a system that created from such a process. So that is one of the challenges, right? That automated execution is not necessarily ideal, but also there's the problem of the bubble of trust that a blockchain gives. So many of these processes interact with the real world. I want to know when a container actually enters into the main port in Malta and when it is lifted off the ship. And these are things that are inputted into the blockchain, or the blockchain might send an instruction to actually execute something. But the big challenge here remains, that there might be the two systems, the real world and the smart contract, might end up very easily out of sync. And if they're out of sync, you end up with instructions being sent or issues being raised when in fact the problem is that the syncing mechanism is not necessarily there. So one thing, the approach we took was a slightly different one. So we thought, it's one thing to try to execute such business process models, but business process models, as I said in the first slide, give us a huge opportunity to analyze the behavior of the different parties. And here, what we have, one big opportunity is that we can actually use the business process model as a specification of what we would like to monitor about what is going on in the real world. And doing so, what we can do is we can build actually monitors using standard runtime verification techniques to observe the real world. So we get events from the real world, and which rather than send back actuation instructions, we just observe. And in case of a violation of a divergence from the business process model we used as a specification, we can raise a flag. And then we can use standard runtime verification techniques to build a solution to handle such monitoring. And in fact, when one looks at the PMN notation and what can be done in terms of monitoring, one finds a pretty straightforward one-to-one mapping, because one has, for instance, that activities correspond to functions in smart contracts, with message flows being implemented through function calls, etc. So there is a clear correspondence between the two, which allows for direct translation from the two. So the approach we took for runtime verification, I mean, the runtime verification world, there are a lot of approaches being used by different tools and different techniques. We took a token-based approach. So the idea is that we essentially keep a token of where in the business process model we are running, and as we go along, we move the token along the business process model. If you've got a parallel composition, you split the token. If you've got a join after a fork, you join the different parts of the token. If you've got sequential composition, when you terminate, you pass on the token to the next activity in the business process model. From a formal perspective, this is great, because this corresponds very, very closely to Petrinets. In fact, one can go almost directly to Petrinet semantics given to BPMN in the literature. And this reduces much of the burden of correctness of the translation, because essentially what we have is an implementation of the operational semantics of for petronets, and a simple correspondence between BPMN or a subset of BPMN and petronets in this case. From a pragmatic perspective, this is also great because the notion of token-based execution is very diffused in the DLT world, and there's a lot of work on handling tokens, on how you can implement things like atomic swaps, like standard token transfers across different blockchains, and we can use a number of these in order to handle the issue of the bridging of trust that I mentioned earlier on. So just to give a taste of what this distribution process across different blockchains, this comes at a cost, right? Now, typically in computer science, we measure cost in, depends on, but usually in time and space and perhaps communication cost. On blockchain systems, typically people use the notion of gas. In terms of cost, the notion of gas is that if you want to execute a smart contract, you need to pay a fee for the execution of the code. The more code you have that you want to execute and the more data you have, the higher the amount of gas that you have to pay for.
Sorry,
And
I don't mean to interrupt you, but you have about 9 minutes left, including questions.
Yes, I'm going to conclude in just 2 more slides, so thank you very much. So what we did was we took a description of a system and put everything on the same blockchain and then split it across different blockchains. Obviously, this depends on the dependencies between them, but one can see that the actual increase in cost in terms of gas here, one can see an increase of less than 10%, I believe something like 8%. So this is the cost of distributing things across different blockchains, which, as we said, in this context can be not a choice. It's a requirement. So we see what we've done as more than anything as a first step in a lot of work that we plan to further the things that we've built. Well, first of all, we've done a lot of work on runtime verification of smart contracts. And what we really plan to do in the coming few months is look at how we can actually monitor not only events coming in from the different processes, but also smart contracts executing parts of things. In this manner, we can have a much more fine-grained approach, and possibly we can use techniques that we've developed in the past to statically verify parts of the code that we would like to runtime verify in order to reduce runtime verification overheads. Also, we would like to join what we're doing with some recent work of ours on triggering external calls from smart contracts on public blockchain systems. And obviously, as I've already mentioned, the notion of checking for correctness of the translation that we are using. So to conclude and leave some time for the questions, what we've presented, I think, is essentially an instance of the challenge of runtime verification of distributed heterogeneous systems. And this is known to be a challenging domain. There is quite a lot of work out there, and this is an instance which shows that the challenges are there. An additional challenge we faced was this idea of islands of trust. So it's not only how to pass on verification and monitoring, but also how to pass on this issue of trust. And although our results are primarily of a pragmatic nature, where we show how things can be done, we believe that there is also a theoretical contribution that we can use this eventually to contribute to. Thanks a lot.